Hello, welcome to this new lecture of this course Transportation Network Analysis. So in the last class we were discussing about logit based loading, so we will continue in that direction. So we will now present the expression for the choice function for this logit choice model. So the probability that the kth route is chosen between OD pair RS is given by this expression here. So it is saying it is equal to e to the power minus theta times CKRS divided by summation e to the power minus theta CLRS, where this summation is all the path L which lie between R to S. So this CKRS, if you remember, is the measured travel time of the kth path connecting R to S. And note that this scaling parameter theta is also there, and that is important because without it the choice probabilities would have depended on the units of measurement of travel time. Okay. So for example, if there was no theta here, then whether you specify CKRS in kilometer or whether you specify it in meter and so on, depending upon what measurement units you use, you will get different probabilities. Okay. For example, if the CKRS is suppose 1 kilometer, okay, and suppose there are only two paths. For the first path CKRS is 1 kilometer, for the second path it is suppose 2 kilometer. Okay. So then if you are computing the choice probability for the first path, then it will be e to the power of minus theta times 1 divided by e to the power minus theta times 1 plus e to the power minus theta times 2. Okay. Now suppose instead of specifying these length units in terms of kilometer, let us specify them in meters. So now the choice probability for the first path will be equal to e to the power minus theta times 1000, because now 1 kilometer is equal to 1000 meters, divided by e to the power minus theta times 1000 plus e to the power minus theta times 2000. Okay. Now these two quantities are not the same, but this is an issue because the probability of choosing a particular path should not be dependent upon what units we use to specify the length of that path, right? So that's why the choice of the units that we use to specify the values of CKRS should not affect the choice probability. So therefore this theta is required, because this will accordingly scale these probabilities. So this theta here then should not be equal to this theta. Okay, if this is theta here, then this should be some theta dash, so that theta times 1 is equal to theta dash times 1000. Okay. Only if these two quantities are the same, then we can expect the choice probabilities to be the same. Okay. So with this let us end this discussion on the logit based loading. So we will now cover some critique of logit based loading. So what are some limitations of logit based loading? So the limitations of logit based loading actually arise because of some of the underlying assumptions that we make while using this choice model. So let us take a look at this network that is shown here. So here we have one origin R and one destination S. Okay. So this is the origin, this is the destination S here. Okay. And there are three paths that are connecting this origin to destination. Okay. Now suppose that the measured travel time on each path is equal to 1 unit. So you can see that for the top path the measured travel time is written, so that is equal to 1. For the second path this is also equal to 1, because 1 minus rho plus rho is equal to 1. Okay. And the same is true for this bottommost path also, its measured travel time is also equal to 1. Okay. So these values are the measured travel time of these different paths here. Okay. Now you can see that the bottom two paths here overlap over a portion of their length which is designated by rho. Okay. So the length of this overlapping portion is equal to rho. This is that overlapping portion for the bottom two most paths. Okay. Now according to the logit based assigned model, the flow on all of these three routes would be equal to 0. Why? Because we will be determining what is the probability of choosing each of these routes, and since the measure travel time on each of these routes is equal to 1, when we will be using this expression for determining the choice probability, so this is what we will be getting. Okay, so we have e to the power minus theta times 1, so that is why 1 is not being shown here, divided by e to the power minus theta plus e to the power minus theta plus e to the power minus theta. So finally we get 1/3. Okay, so the probability of choosing each of these three paths is equal and is equal to 1/3. Okay. Now this kind of assignment might seem reasonable if the amount of overlap rho is relatively small as shown in the following figure. So if for example we are using this logit based loading model, okay, and we are dividing the probability of choosing these different paths here. So this kind of values that every path will get selected with 1/3 probability, so that might seem reasonable if you have this kind of figure where this overlapping portion rho is very small. Okay, but this kind of distribution of the flow across these three different paths, that is assigning equal flow to all of these three paths, will not be correct if this overlapping portion is very large. So this is that example here. Okay, and why is that the case? Because in this case, when the overlapping portion rho is very large, the travelers may perceive the bottom two routes as a single alternative. Okay, because since this portion which is separating these two bottommost paths, this is very small, and for most of the portions of these two paths they are the same here, because rho is this overlapping portion here. So actually people who might be starting to travel from origin R might think that they are the same paths. Okay, and that is not a wrong assumption to make, right? And this will surely be the case when the limit rho goes to 1. Okay, so then in this case each of the remaining paths will carry 1/2 of the flow. That is, when this portion is very small, almost going towards 0, that is rho is going towards 1, so then what ideally we should see is that half of the flow should be assigned to this topmost path and half of the total flow should be assigned to these bottom two paths, because effectively these two bottom paths are the same path. Okay, because this overlapping portion is almost going towards 0. Okay, but the logit model, even in that case, will be assigning 1/3 flow to all of these three paths. Okay, so in this kind of case, when rho is going towards 1, this logit model is overestimating the flow on the overlapping paths. So it is trying to give a total of 2/3 flow to these bottom two most paths, whereas ideally it should only assign half of the flow to these bottom two paths. Okay, so this is an error that is arising because of the use of logit based loading model in this example. Okay. Now the deficiency of this logit model results from logit's inability to account for correlation between the alternatives' utilities. So if you remember, when we determined the error distribution for this logit model, so there we had assumed that the error terms are IID Gumbel variates, that is they are independently and identically distributed. Okay, so when we are having this independent distribution, so that means that the error value for each of these alternatives is coming from a same distribution across all of these alternatives. Okay, although this value that is coming for each error term is independent. Okay, for example, if suppose we have some kind of distribution, okay, for the error term, suppose this is the distribution of how the Gumbel variates vary. Okay, so when we have different alternatives, for the first alternative we will randomly pick one value from this distribution. Okay, now for the second alternative we will again randomly pick a value from this distribution. Now the second value that we have picked for the second path's error term, so this is totally independent of what value was picked for the error value of the first path. Okay, so in that way the error values that we have for these different alternatives, or in this case different paths, they are independent of each other. Okay, and since the perceived utility of any alternative is equal to the measured utility plus the error term value that we have, and the measured utilities are given values, those are fixed values, deterministic values. Okay, so therefore if any correlation has to happen across different alternatives utilities here, so that has to come from the correlation between the error terms. Okay, and since the error terms across different alternatives in Logit model are assumed to be coming independently, so therefore there cannot be any correlation between the alternatives utilities if we are assuming a Logit choice model. Okay, so this is saying the same thing. This inability stems from the independence assumption about the utilities random components. Okay, so the perceived travel times on the bottom two paths are correlated by virtue of their overlapping segment. Okay, so since a large portion of these two bottom paths are overlapping, okay, so if we see that the perceived travel time of one of these bottom paths is suppose very high, then the perceived travel time of the other bottom path should also be very high, because they are having a very high overlapping segment. Okay, because it is very likely that this error term is very large for one of the bottommost paths, and since both of these two paths have a very large overlapping segment, so the other path should also have a very high value of this utility value. Okay, so this is what it is saying. Suppose if a traveler perceives one of the bottom paths or routes to be faster than it really is, then this traveler is also likely to consider the other bottom route as faster. Okay, and the reason for that is the error may be in the perception of the travel time on the overlapping segment, in which case both the bottom paths would be affected. Okay, so the error in the perception of the travel time might be coming hugely from the overlapping segment. Okay, and since that overlapping segment is common to both the bottom paths, it is expected that if the perceived travel time of one of these bottom paths is very high, the perceived travel time of the other path will also be very high, and vice versa, in the sense that if the perceived travel time of one of the bottom paths is very low, so then it is expected that the perceived travel time of the other path will also be very low. Okay, so these two will have to be correlated of each other. They cannot be independent of each other, which will kind of be assumed if we have a Logit choice modeling here, because there it is assumed that the error terms are independent of each other. So therefore when we have these total perceived utility values, so they cannot be correlated with each other. Okay, so this extent of this correlation is determined by the relative length of the common segment. Okay, but the Logit model cannot consider this due to its independence assumption. Okay. So this is what we have been saying, since the logit model assumes that the error terms are coming from independently from the same Gumber-Berry distribution. So it is just not possible that these error values have some correlation between them. Okay. And since the perceived utility is equal to the measured utility plus the error term, and the measured utilities are anyway deterministic and given values, so whatever correlation has to happen between the utilities of two alternatives, it has to happen because of the correlation between the error terms of those alternatives. Okay. Okay, so this was one of the limitations of the logit model. Let us take a look at another limitation of this logit model. So take a look at this diagram here. There is one origin and one destination. Okay, but then there are two cases here. In this first case, there are two paths connecting origin to the destination, and here one of the paths has measured travel time equal to 5 minutes, and the other path has measured travel time equal to 10 minutes. Okay. And in this case, the measured travel time of one of the paths is 120 minutes and the measured travel time of the other path is 125 minutes. Okay. So a key thing to notice here is that the difference of the measured travel times of these two paths is equal to 5 minutes in this case also, and it is equal to 5 minutes in this case also, because 10 minus 5 is equal to 125 minus 120. Okay. Now in this case, that is the leftmost case here, it is likely that most of the travelers will choose the 5-minute path. Okay. Whereas in the right case, a significant number of travelers will choose the longer 125-minute path rather than the 120-minute path. Okay. So although the difference of the measured travel times in these two cases is the same, that is, it is 5 minutes, it will not happen that if suppose X percentage of the people are choosing 5 minutes here and 100 minus X is choosing 10 minutes, it will also be the case that X percentage of the people will be choosing this path that has 120 minutes as the measured travel time, and 100 minus X percentage of people will be choosing this path that has 125 minutes of measured travel time. Why? Because it can be clearly seen that people will not be differentiating this 125-minute path versus 120-minute path that much, okay, as they will be effectively be able to differentiate this 5-minute path versus 10-minute path. Okay, that is, in terms of perception of the travel time, there will be less variance when they are comparing this 5-minute path versus 10-minute path, whereas that perception variance will be higher when they are comparing 120-minute path versus 125-minute path. Okay. So this is what is being said, this expected path choice behavior is due to the variance in perception, which is likely to be related to the length of the paths. Okay. So when these two choices are being compared, that is, you have two paths, one is having 125-minute path and the other is having 120-minute path. So then the perception in the travel time, that will have higher variance when you are comparing this versus this here, because these two might be perceived to be very similar paths. So people might almost choose this as equal as this. So the likelihood of choosing this path might be as close as choosing as this path, whereas it might not be the case here, even though the difference of the measured travel time across these two paths is the same. So that is what it is saying, the right case here offers more opportunity for wrong perception in the sense of choosing the longer travel time path. Okay. So the perception of the travel time will be having larger variance in this case here. So as compared to what people might perceive here. Okay. However, if we will be using the Logit based model to decide the flow across these two paths here, in both of these two cases, we will be getting the same flow pattern, as the choice function is dependent on the difference in the measured utilities. Okay. Why is that? If we see, for example, what is the probability of choosing the first path, it is equal to this P1, which is given by e to the power of V1, where V1 is the measured utility of this first alternative, that is the first path, divided by e to the power V1 plus e to the power of V2. Okay. Now, if we divide both numerator and denominator by e to the power of V1, this is the expression that we will be getting. Okay. Now, you can see that this expression is only a function of the difference of the measured utilities V2 minus V1. Okay. Now, you must remember that V1 will be equal to what? It will be equal to minus of theta times of the measured travel time of the first path. Okay. Similarly, V2 will be equal to minus theta times the measured travel time of the second path. Okay. So, the difference of these utilities is also proportional to the difference of these measured travel times on these two paths. Okay. And since the difference of the measured travel times in these two cases is equal to 5 minutes, so therefore, this probability P1 will be coming out to be the same here as well as here. So, the probability of choosing this 5-minute path is coming out to be the same as the probability of choosing the 120-minute path in both of these cases, if we are assuming that the flow distribution is happening based on Logit model. But in the real world case, we can assume that people will be differentiating and choosing this 5-minute path more over 10-minute path as compared to choosing this 120-minute path over 125-minute path. Okay. Because since this length is very long, I mean the lengths of these two paths, 125-minute and 120-minute, so people will not think that this is too short a path as compared to this 5-minute path versus 10-minute path. Okay. So, this is rooted in the Logit's underlying assumption that the utilities error terms are identically distributed with same fixed variances. So, if you remember, this error term in the Logit choice model is assumed to be IID Gumbel variate, that is, it is having independent and identical distribution from the Gumbel variate. Okay. So, since this identical term is there, so that means that the error terms of these different alternatives are coming from the same distribution. Okay. And also this distribution has a standard variance that is associated with it, okay, which is given by this distribution of the Gumbel distribution that we have. Okay. So, these variances are fixed for every error term, they cannot change. Okay. Those are some standard values. Therefore, this Logit model is not applicable in cases where the error terms distribution depends on the alternative's characteristics or on the systematic part of the utility functions. So, in this example that we saw, actually the error distributions should have had the variance to be function of what is actually the measured travel time on a given path. For example, when the measured travel times were very high, that is when they were 120 minutes and 125 minutes, the variance of the error terms in that case should have been higher, whereas the variance in the error terms would be lower when we have this case of 10-minute versus 5-minute. Okay. But that kind of differentiation of having different kind of variance in the error distribution is not allowed when you assume Logit choice model. Okay. So, this is what it is saying in the above example, the distribution of the perceived path travel times should be a function of the respective lengths of the alternative routes. Okay. I mean, this should ideally be the case, but then this is not allowed if you are assuming Logit choice model. Okay. But these two kind of limitations that we have seen for the Logit choice model do not cloud the fact that there are some efficient algorithms such as stock to implement Logit based algorithms. Okay. So, although we do not have time to cover these kind of algorithms here, but there are some algorithms which can actually mimic this Logit distribution. Okay. So, although we have seen that we can determine the choice probabilities of different routes using that expression that we have, but remember that when we are using that expression, we need to enumerate all of the paths, because the probability of choosing the first path is equal to e to the power of the measured utility of the first path divided by sum across all the paths e to the power the measured utility of that given path. Okay. So, in the denominator we are doing the sum over all of the paths that are possible between these given OD pair. Okay. Now, if we have to sum across all of these paths, that is we have to go through all of the paths, then that is called enumeration. Okay. And even listing down all of these paths in a very complex network between a given origin to destination might be very computationally burdensome process. Okay. So, since we have discussed this terminology called polynomial time algorithms, we can just briefly say that in some of the very complex networks it might not be possible to determine all the possible paths between a given OD pair in polynomial time. Okay. And therefore, if someone is using this Logit choice expression that we saw to determine the choice of choosing any particular path, so then you will have to enumerate across all of the paths, and that itself might be a very computationally burdensome process. Okay. So, therefore, there are some other efficient algorithms such as stock which do not require enumeration across different paths. They do some assignment of flows across links rather than paths, and automatically that leads to the assignment of flows on the paths also. Okay. So, this algorithm is also discussed in Yosef Shafi's book on urban transportation networks. So, if anyone is interested, you can read that. Okay. So, what we want to say is that Logit based modeling can be implied very easily because of the presence of these efficient algorithms, and Logit based model remains popular as it works well for the cases where the perceived utilities of the alternatives are only slightly correlated and when their probability distributions are similar. Okay. So, when we have that case where the perceived utilities of the alternatives are having very less correlation, okay, so they can be as good as assuming that these perceived utilities are independent. Okay. And also, if we have this thing that the perceived utilities of the example that we are considering are having very similar probability distributions. Okay. So, in that case also, then assuming this Logit model is not bad, because then that assumption of identical distribution for the error terms can make sense. Okay. So, under those situations, using Logit model is not a bad choice, because Logit model has its own advantages, that is its choice probability is having closed form expressions. There are also other efficient algorithms to calculate these choice probabilities. Okay. Okay. So, this was the discussion regarding the Logit based model. Now, let us discuss some another kind of loading model called Probit based loading model. So, if you remember, when we had tried to calculate the choice probabilities or the satisfaction function for the Probit based loading model, so there we had gone back to this Monte Carlo simulation. Okay. So, we will be doing something similar here also. So, the idea in Probit based loading is that in each iteration of this Monte Carlo, the density function of the perceived travel time of each link is sampled once. Okay. So, suppose you have a network here. Okay. Okay. So, now suppose we know that the link travel time of each link here is having some distribution. Okay. And it will be assumed that these distributions are normal. Okay. So, the distribution of the perceived travel time of each link is shown here. Okay. It is given. Okay. So we will be sampling the values of the perceived travel time of each link, okay, once in every iteration of the algorithm. So suppose this is one value of the perceived travel time that we get for this link. Suppose this value comes out to be 1, this comes out to be 2, suppose this comes out to be again 2, this comes out to be 3, and this one comes out to be 4, okay. Let us make this one as maybe 3, okay. So these are the sample values that we got for the perceived travel times of different links here, okay, in this iteration. Now what we do is that we do all or nothing assignment in this iteration of the Monte Carlo. So in every iteration we will be doing all or nothing assignment. And why is that possible? Because once we have sampled these values of the link travel times from the perceived travel time distribution, so then these values are some fixed values, these are constant, okay. So these 1, 2, 3, 4, these are constant values, okay. So now if suppose this is the origin R and this is the destination S, so we can then do all or nothing assignment here, because we now know that there will be one path which might be the shortest. So for example, this path, top one is the shortest because this 1 plus 3 is lesser than 2 plus 3, okay. So therefore we can assign all of this flow that we have to this path, okay, in this iteration of the algorithm, okay. So the flow is between each OD pair is assigned to the shortest travel time path between that OD pair, okay. And this process of sampling and assignment is repeated several times, okay. So this is repeated many times. So it might be the case that some other path might turn out to be the shortest in some other iteration of the Monte Carlo simulation, okay. So what we will be doing is that we will be then averaging out all of these flows across different links in these different iterations, okay. So for example, for a particular link, the value you got for a particular iteration is suppose 1 unit of flow in one iteration. In the other iteration, suppose you get 10, then 5, suppose there are 3 iterations, okay. So the average flow on the link for that case is 1 plus 5 plus 10 divided by 3, okay. So you do this for all of the links, okay. So in that way we get the average flows across these different links here, okay. And this process is terminated, that is how many iterations of the Monte Carlo should we do, that can be dependent upon when we think that by doing further iterations we are not seeing the change in suppose the average link flow, okay. And it is also possible that the sampling of these perceived travel times might yield negative perceived travel times, because these link travel times that we have, they are coming from normal distribution, okay. So normal distribution also takes negative values, so those things might also arise. But then if the distribution is such that the negative part is very small, and if we discard those negative values, so then we can kind of ensure that we are only taking the positive values, and if that negative portion in the distribution is very small, so then it will not make any difference, okay. Okay, so with this we will be continuing this Probit based loading in the next class. Thank you.